Thank you very much for the opportunity to be here. I'd like to thank the Chubb family for sponsoring this lectureship, and thank you for coming tonight to hear this. My lecture is going to be in two parts, and in the first part, I'm just going to go over with you the fundamental science, the physics really, of what underlies our understanding of climate change. And I want to do that because there's still a lot of confusion about it, and often it's not completely understood. And we'll also do some history, and I think you'll see how long it is that people have been thinking about this problem of climate change. Sometimes when you read the newspaper or the magazines, you might get the feeling that, oh, scientists just came across this idea. But I think what you'll see is that it's an idea actually that traces its roots over almost 150 years. And so you'll see kind of the evolution of it. And in fact, one of the big themes of this lecture will be that at each stage when a new discipline of physics developed, it very quickly ended up impacting our thinking about the planet. And it informed our understanding about climate. And so our understanding today about what is happening with respect to climate change is actually rooted in the core of physics. So let's go into just a couple of quick statements at the beginning about the carbon cycle. Of course, in the natural world, without anthropogenic or human activity, there is a carbon cycle, and it's got two parts to it. It's got a biological piece and a geological or earth kind of piece, in the sense that, for example, as living beings are dying, they'll release carbon matter, CO2, into the atmosphere, and of course plants will also pull CO2 out. And so there's a rapid time scale, annual kind of cycle that's associated with the biosphere. But then there's the sort of geological time scale. If we have a volcanic eruption, that volcanic eruption will put a lot of CO2 into the atmosphere. And in the long term, if the CO2 in the atmosphere is perturbed away from its normal equilibrium value, it's actually ultimately the geological cycle that can restore it. And that happens because CO2 can enter the oceans. There's sedimentary processes that can create the rocks, and of course then they can cycle again through volcanoes. So that's the geological cycle. The biological one tends to be a fast cycle that's really in balance, and the geological one is the one that can kind of restore perturbations. Of course, today, when we burn our fossil fuels on a massive scale, it turns out that about half, when we burn a hydrocarbon and it makes CO2 in water, about half of the CO2 that is released into the atmosphere stays in the atmosphere, and about half of the CO2 that comes from burning fuel enters back into the oceans and into the land. So that's a perturbation which over time is causing CO2 to build up in the atmosphere, and we're going to see more about that. And so what we need to do in the science world today is to try to think about really something that has never been done by humanity before. It's actually to think about how to create a stable cycle for carbon in the presence of human activity. And that is human activity not just as it is today, but as it will be in coming generations when many, many more people on the planet have access to energy. Today there are 2 billion people on the planet who live for $2 or less a day. That's their income. And those people have very little access to energy. But as time goes on, they're getting more and more access to energy. So our energy use is increasing over time. And so we need to be able to design a future carbon cycle where it's still in balance. What we produce in terms of extra carbon is actually also consumed somehow, and those two are equilibrated with each other. And that's something which, operating on a planetary scale, as I said, has really never been done before. So it's a very interesting moment. Now, let me start by saying, it's been studied a lot, and if you just read some of the current literature, you'll see a bunch of papers, for example, that are cited here. A bunch of different authors try to say, well, there's some change in what's going on to the temperature of the Earth. What does that due to? Is it due to people, or is it due to natural things? And so these bunch of authors here, they all come up with some slightly different percentage there, but you can see there's sort of, the experts are sort of all saying, looks like people are changing the temperature. And I don't know if you followed in the last election, in the presidential election, Nate Silver, who of course ran all of the polls, did the statistics on all of the polls. He's an expert on statistics, and he's written an interesting book. You might want to read it, called The Signal and the Noise. And in there, he has a chapter on climate change. It's an okay chapter. And one of the things that he says in there, which I think is really spot on, is that predictions, you try to make predictions based on what you see happening. You parse all the data, all the information comes in, and you try to figure it out. But when you're trying to make a prediction, it turns out that if you have a sound understanding of the underlying principles according to which a system operates, then your ability to make predictions about the future are much greater than if you're just getting information coming at you from all sides, but you don't understand how the system really works. Okay? So we need to do that. We need to understand what is the physics of the greenhouse effect, where does it come from? And if we understand that, then we have a context by which we can try to parse all the information that's out there. If you're just reading, you can see all kinds of articles and information coming at you. Okay, so here you can see a first piece of evidence that will start our story. This shows the concentration of CO2 in the atmosphere as a function of the year, starting from the year 1000 roughly, and then going through up to the present day. And what you can see is, it looks like it's holding pretty constant, and then all of a sudden it starts to take off. Okay? And so it's a reasonable question to ask, right at that point where it started to take off, where was that in time? Well, it turns out that was really in 1769, which was the year when James Watt developed the first practical steam engine. In other words, it marks the moment when the Industrial Revolution really started. And from that moment, you can see the concentration of CO2 in the atmosphere starting to take off. Now, it turns out it's interesting that it was the heat engine that was the key piece of technology, because if you think about it from a physics point of view, many of you here have studied physics at different times, what you know is, in order to make a good heat engine, you had to develop a certain field of science, thermodynamics. And it turns out that that is actually going to be the first thing that we're going to need to do in order to understand the temperature of the Earth. We're going to need to use a little bit of thermodynamics. So we're now going to proceed. We're going to answer 3 questions, relatively short order. Does an increase in atmospheric CO2 influence the Earth's temperature? What is the principle according to which that works? Is CO2 in fact increasing? And is that increase due to human activity or something else? And the third question, couldn't we simply adapt to any changes that might arise in CO2? Okay, so those are the 3 questions we're going to go through. Okay. Now, as I mentioned to you, there's a long history of this question. This is not something that just has popped up out of nowhere from the world of science. In fact, it's rooted in the core disciplines of science. And so we're going to see here how 3 great giants of 19th century science have laid the foundations for our understanding of how climate change really is coming about. So we're going to start with Fourier. Fourier was a physicist and mathematician. Many of you may have encountered his methods of mathematically doing Fourier transforms and other things. But what Fourier was principally occupied with was trying to understand the science of thermodynamics. In other words, how does a hot body transfer energy to a cold body? Okay. And that's, of course, a science which was essential to developing heat engines and to developing the industry of his era. That's why they were trying to do it. But in fact, there was a very famous problem that arose during the period of Fourier's research, which was how to calculate the temperature of the Earth. He was the first person that tried to calculate the temperature of the Earth by saying, okay, there's the sun is hot, and there's the Earth is cold, so the hot body should transfer heat to the cold one and warm it. Okay? Now, of course, the Earth is also sitting in the middle of cold nothing, and so the Earth itself can also transfer heat away. So energy will be coming from the sun to the Earth and warming it, and energy will be leaving the sun, leaving the Earth and cooling it. And the balance between that heating and cooling you could use to ultimately calculate the temperature of the Earth. And he knew thermodynamics. It's a great discipline. It was accurately predicting how two bodies that were in the laboratory would connect with each other. So he wanted to apply it to the sun and to the Earth. He calculated the temperature, and the temperature came out wrong by about 20 degrees Celsius. The Earth came out too cold in his calculation. This was the theory that was working for everything else that was going on, where you were trying to calculate temperatures. That stuff was all working great. So the question was, what could possibly be going wrong here? And 20 degrees, by the way, is an enormous temperature difference. It would correspond, if we were 20 degrees colder, it would be absolute snowball Earth. Okay, everything would be frozen. And of course, we know that's not the case. And so why was it? Why couldn't he get that right? And Fourier was the person who ultimately realized that it was the atmosphere that controls that. And what he explained was that when visible light leaves the sun and comes and hits the Earth, it's absorbed, it heats the Earth. The Earth can radiate out towards space, cooling, so there's a heating and a cooling, and the balance between those creates the temperature of the Earth. But the atmosphere itself, he reasoned, must do something to trap heat around the Earth in the same way that a blanket, for example, if you're in bed and you wrap yourself in a blanket, it's your own heat that's keeping you warm by trapping it in. It must somehow be that the atmosphere is doing that. Now, of course, he had no way of knowing the mechanism by which that happened, because at that point in time, that science was not yet developed. But he understood that there had to be such an effect going on, and that's when the term greenhouse effect was first coined in 1827. The next step in this was actually to understand the mechanism by which the atmosphere actually could contribute to the heating of the planet. How does the atmosphere contribute in that way? And it turns out that this has to do with the development of another very important field of physics, spectroscopy, or how light interacts with matter. And in this case, what was going on was John Tyndall was studying a set of gases in tubes. He could take a pure gas like water, put it in a tube, and send different colors of light through the tube and see if they came out the other end. And what he found was that depending on the color of the light, sometimes it would be very strongly absorbed. And that light was infrared light, not visible. So visible light comes from the sun and hits the planet. Infrared light is sent away from the planet, cooling it. And what he found was that various gases, for example, water and CO2, would selectively, specifically absorb energy at very particular frequencies. And what would happen, this was the origin, ultimately, of our understanding of vibrational spectroscopy, of how molecules vibrate when light excites them at particular frequencies. That was the first observation with John Tyndall's in 1859. And of course, he was very well aware of Fourier's problem of trying to calculate the temperature, and so he realized immediately that this was the basis, actually, for the greenhouse effect. And he said in this kind of 19th century prose, as a dam built across a river causes a local deepening of the stream, so our atmosphere, thrown as a barrier across the terrestrial rays, produces a local heightening of the temperature at the Earth's surface. Now, he also said, because there's a lot of water in the atmosphere and there's a lot of carbon dioxide both, and both of them could absorb infrared light, So he said, without water, the Earth's surface would be held fast in the grip of frost. Actually, it turns out, as you'll notice here, that the wavelengths at which water and CO2 absorb are not the same. And you'll see that the CO2 here absorbs in a window where water does not. And it's certainly the case, as you'll see as we go through this, that there's a plentiful, abundant amount of water in the atmosphere. And there's only a very small amount of CO2. So at first you would think, well, it must be that water ultimately controls the temperature. But in fact, what we're going to see in what follows is that over time we've learned that CO2 is actually a fundamental control knob for the temperature of the Earth. And it took a little time for scientists to understand why that is. We're going to go through that now. So the next really remarkable development of this is actually the single most famous and impactful paper in the history of climate science. Okay? And this is a paper written by Svante Arrhenius in 1896. Arrhenius, a Nobel laureate who studied the kinetics of chemical reactions, how one molecule transforms into another, and developed a model for that that's widely used to this day, the Arrhenius law. So Arrhenius was in the Swedish Academy, Royal Academy, and he had a friend who was a climate scientist, and his climate scientist friend wanted to understand what led to ice ages. Okay, so it was well known that there had been in the past periods when the planet was frozen and periods when it was warmer, and they wanted to understand how come sometimes it was cold and sometimes not. Where did that come from? And about the work of Fourier and Tyndall and others, so they knew that potentially CO2 actually could have potentially controlled the temperature. And they didn't know for sure whether it could or not, so he did a famous calculation. He did a calculation where he said, well, first of all, he did an experiment. He found a very tricky way of using light bouncing from the sun off of the moon through the atmosphere to measure the concentration of CO2 in the atmosphere. So he produced the first known measure at around just under 300 ppm. He found the first measure of the concentration of CO2 in the atmosphere, and then knowing that, he also thought, okay, I'll do an experiment where I'll just imagine that I'll take away half the CO2 in the atmosphere, and I'll recalculate the temperature of the Earth, and I'll see what will happen. Will the Earth get colder? Because it would change the greenhouse effect. And while he was at it, he also said, okay, I'll also, just for the fun of it, well, not for the fun of it, he saw that there were all these factories going on that were burning fuels and putting CO2 into the atmosphere, and he thought, okay, I'll calculate what would happen if I doubled the CO2 in the atmosphere as well, and just see what happens to the temperature. And so he performed the first calculation. It was a laborious and difficult calculation for a variety of reasons. And he calculated it, and he got, in his first version, that the temperature would go up by 5 degrees Celsius. Later, he refined his calculation and got 2.1 degrees C. Actually, if you ask scientists today, what is the so-called climate sensitivity? In other words, if you double CO2 in the atmosphere, how much will the temperature change? They'll say, I can bracket it at somewhere between 2.5 and 4.5 degrees Celsius. Okay? So it turned out Arrhenius in 1896, now, there were reasons actually to think about this as having problems as well. And you may have heard of another famous name in science, angstrom. Angstrom is a unit of length. And the son of angstrom, who found the unit of length, shortly after Arrhenius' paper, raised a conundrum. And he said, I don't think this Arrhenius calculation can be quite right, because there's, when I really think about how light gets absorbed, and it turns out there's some tricky concepts in this, when I really think about how the infrared light would get absorbed as it reflects off of the Earth, there's so much CO2 in the atmosphere that in fact it will be saturated. and it won't matter. I could put in as much CO2 as I want, and the infrared light will never make it out. So there was a little confusion. There was a period of trying to figure this out. And we're, in a moment in the slide, I'm going to show you how that really works out. Now, here you can see what we know today. The true, this is the emission of visible light by the sun, and then this is the outgoing light from the Earth that's at a much longer wavelength. So this is what comes in and hits the Earth and warms it. This is the radiation leaving the Earth that cools it. And you can see here the absorptions from many different gases. For example, here's the water vapor, which is saturated. When you see these things go flat top, that means that you can put more water in there. It won't make too much of a difference. But you can also see this critical window here in between the two big water absorption peaks, where there's a strong absorption by carbon dioxide. And it turns out this little absorption of carbon dioxide in this window is what makes carbon dioxide such a potent greenhouse gas, because it's acting where the water is not. So the water is saturated, but small changes in CO2 actually affect this window. And this is a window where the planet Earth can irradiate away infrared light. And if instead there's a lot of absorption going on there, then that retains heat and warms the planet. Now, I mentioned to you this little conundrum in there about the issue of how optically dense, how thick is the CO2, and how do we get the temperature right. And it turns out there is a slightly more detailed calculation that has to be done to get this part right. And it goes something like this. Visible light comes through and hits the Earth, and then the Earth warms up and it sends out infrared light, and the infrared light does indeed get absorbed by the atmosphere, and some of it will be radiated back outwards, and some of it will be radiated down. And then, if I think of the atmosphere as consisting of many, many layers, then this layer will radiate down, and this one up, and down, and up, and down, and up. But it turns out, at the very top of where there's almost no CO2 left, okay, then there's a final layer. And that final layer, actually, when it emits a photon of infrared light, it just escapes. So it's that final layer which is actually responsible for the cooling of the planet. Okay? Now, what happens when you put more CO2 into the atmosphere is you push that height of that final layer to a higher altitude. And you will presumably recall that as you go up to higher altitude, the temperature drops in the atmosphere. It gets less dense. Those are the gas laws. So if the planet is cooling itself from a lower temperature, its cooling efficiency goes down, and therefore the temperature of the planet goes up. So in the end, Angstrom's concern turned out not to be correct. It took a lot of discovery to find that, but by 1927, this was a settled issue. What I just showed you. Now, I mentioned to you that CO2 turns out to be a control knob. Here you can see a simulation that kind of shows that. Remember, the atmosphere has tons of water in it. That's really saturated. But that CO2 is very dilute. There's not a lot of it. And there's one big difference between water and CO2 as important greenhouse gases. And those have to do with the fact that water can be frozen out. And CO2 in the relevant temperature range of the planet does not. So in this simulation, what you see is they just simply, on the computer, took out all the CO2 and said, what will happen to the temperature? And what will happen is, actually, the Earth will freeze, and the water will all become frozen, and you just get snowball Earth. Okay, just all frozen. So if all the CO2 were suddenly removed from the atmosphere, our planet would have no liquid water. It would all be ice, everything frozen. Okay? That's why we can think of CO2 as the control knob, because CO2 has no phase transition like that, whereas the water does. So what I'm trying to show you in this first part is that fundamental aspects of physics, it turns out I didn't go into the statistical mechanics part, but you can kind of imagine there are wings to those absorption peaks, and those actually map to treat statistically and so on. But thermodynamics, statistical mechanics, quantum mechanics, molecular spectroscopy, those four topics together are what you need to calculate the temperature of the Earth in the presence of the change of CO2. And in fact, what I would say is our knowledge of those 4 disciplines says that that is what happens to the planet. So if we go back to Nate Silver's thing, it's not like we're dealing with disparate observations. We have a fundamental understanding that leads us to understand why it is that the planet's temperature depends so much on CO2. So it's easy to answer the first question. Does an increase in atmospheric CO2 influence the Earth's temperature? The answer is yes, definitively, absolutely no, beyond any possible question. So, is CO2 increasing? And is that increase due to human activity? Well, so this is a famous experiment called the Keeling curve. Keeling, in the year of, in 1957, it was the year of the Earth, UN year of the Earth, and there were a bunch of, and he was trying for many years, they knew, of course, for a long time that CO2 could be an important gas. Keeling was trying for several years to be able to establish an experiment where he could measure the CO2 concentration in the atmosphere on a regular basis. And finally, during that UN year of the Earth, he succeeded in getting a grant funded, and he was able to establish in Mauna Loa a measuring site where he could measure the CO2 in the atmosphere. And ever since then, it's been there measuring it. Of course, nowadays it's measured in many other locations. But what he saw was a couple of interesting things. This is the increase. The red curve shows the average concentration of CO2 in the atmosphere as a function of the time, and you can see it going up. But you'll also notice these oscillations. This is what the data really does. And these are the annual oscillations of CO2 in the atmosphere. Where do those come from? Those, of course, come, it's as if the planet is breathing. In the summer months, the CO2 in water is taken up by plants, and it makes a lot of biomass. In the winter months, the plants die and release CO2. So every year you can see the planet breathing CO2 in and out, okay? And that gives you a calibration sense. You know, there's an enormous change in the biosphere that goes on each year, and you can see that the increases, the increase in CO2 over time is larger than those oscillations of what the planetary biosphere is doing. So this curve kind of calibrates itself in a sense. That's CO2. Now, this is kind of a fathers and sons talk because Dave Keeling, who did the original Keeling curve, his son Roger, decided some years later to measure what happens to oxygen. Well, let's think about it. I take a hydrocarbon and I burn it, then what will happen is I'll make CO2 and water, okay? But to burn the hydrocarbon, I need to consume oxygen. So from elementary freshman chemistry, I know that if I take a hydrocarbon and burn it, I have to consume oxygen in proportion to every molecule of methane, for example, that I would burn. So Roger agreed, I could go and measure the curve for oxygen in the atmosphere. And so this is his curve. It doesn't go back as far, but this is the oxygen actually decreasing in the atmosphere as a function of the time. Now, don't worry, you're going to be able to breathe just fine because the base concentration of oxygen is about 20%, and the concentration of CO2 in the atmosphere is only changing by a few parts per million every year. 3 or 4 parts per million each year it goes up. And accelerating, but so it's a small percent change, but it's quite detectable, and again you can see those oscillations, and so we know that it's a combustion process, we know that it's a combustion process that's producing the increase in the CO2 because we can mass balance with the oxygen. Another experiment that can be done is to look at the isotopes. It turns out that plants will take oxygen out of the atmosphere in order to respire, and so they will tend to selectively assimilate lighter isotopes during photosynthesis. And so you see that here. What you can see is that selectively over time, the C12 is enhanced in plants. Now, when we burn fossil fuel has its origins as plant matter, which over time became the fossil fuel. Okay? And so when we burn fossil fuel, we enhance the amount of carbon-12 in the atmosphere because there's more carbon-12 in the plants. And so this is a kind of isotopic method of showing that it's really fossil fuel combustion that leads to the increase of CO2 in the atmosphere. And we can look now over time, and what you can see is not just, when I showed you earlier, we saw 1,000 years of CO2, but here you can see 800,000 years of CO2 obtained from isophores, and you can see this kind of pattern that's kind of noisy, and so occasionally it's down around 200, occasionally it might get up close to 300 parts per million in the atmosphere, and then you come to the modern era, and you can see that it's gone way up higher. It's approaching 400 parts per million. So that's a region that CO2 has not been in for hundreds of thousands of years through many, many ice age cycles. In fact, one of the things that is most concerning to the scientists who think about these things is the abruptness of the time scale of the change. And that's shown here. Here you can see this period of coming out of one of the glacials, and then you can see this abrupt anthropogenic change, which is happening on a time scale that's so this will happen on time scales of, say, tens of thousands of years. This is happening on a time scale of tens of years. So the difference in the time scales is a factor of 1,000 or so. So nobody completely knows what happens to the planet when you change a parameter like that that controls its temperature in such a short period of time. So is CO2 increasing, and is that increased due to human activity? The answer is yes. Can we simply adapt? So first of all, here is the actual temperature increase of the, not the CO2 now, but this is the temperature increase of the planet. We expect it to be going up because the CO2 is going up, and we know that CO2 is a control knot, and that's in fact what's being seen here. This is the real experiment. And again, what's striking is, these are these sort of long-term kind of excursions that go on, and then here you can see in this incredibly brief period of time, this very quick change in the temperature. Of course, now there's very detailed models that people try to construct that include every possible effect that you could imagine. And so what you see on here are a whole bunch of different computer models. Each one of these yellow curves is a different computer model that tries to reconstruct the temperature as a function of the time. And then you can take kind of the average of all of those, which is this red curve, and then the black curve shows the actual observed temperature as a function of the time. Now, this includes all the effects that we know that could influence the temperature in this curve here with the yellow. And then this blue curve is one where on the computer you just go out and subtract out the anthropogenic effects. In other words, anything having to do with greenhouse gases like CO2, methane, and others. When we subtract all of those out, then you can see this clear difference where the temperature of the planet is increasing. Now, it does turn out that there's one thing you really have to think about. What happens when you put a lot of extra CO2 into the atmosphere is you change the rate at which so the sun is heating the planet, but you've reduced the rate of cooling, so the temperature is going to go up. But how long is that going to take? Well, you know that, for example, if you have a pot of water that's on your stove, okay, that it will take a certain amount of time for it to heat up and get hot. It's being heated by the stove, it's being cooled by, again, radiating, and those balances, eventually you'll get to a new temperature, you can lower your water, but if it's a bigger pot, it will take a longer time. Well, that's sort of what's going on with the planet. We're slowly heating it, but the Earth has a lot of heat capacity. So it will take time for the temperature to completely track what's happened to the greenhouse gases. And that's what we're seeing now. The temperature's increasing, but it's increasing mostly now over land. And the oceans, which have a lot of heat capacity, are slowly heating up. But over time, tens of 100 years or so, the ocean will ultimately reach the temperature which is correct for the amount of heating and cooling that's going on, and the system will equilibrate for what that CO2 concentration is. But for now, we're seeing a lot of heating over the Earth, and the ocean is slowly catching up. Now, what would happen if one day we just said, okay, we'll stop putting any more CO2 into the atmosphere? How long would it take for the CO2 to come back down to the levels that were there before anthropogenic activity? And if you recall, I mentioned to you earlier, there's two aspects to the carbon cycle. There's the biological one, which is very fast, and the geological one is very slow. And it turns out it's ultimately the geological time scale which will restore the CO2 back to where it had been. So if we stopped emitting CO2, it would eventually come back, but unfortunately, it would take a very long time. These calculations on here also show what would happen if, for example, we took all the coal that exists and just burned it all. Right? And so if you did that, well, some people advocate that. And if you did that, if you did that, we would definitely be in the ice-free Earth model for a really long time. So, not recommended. Now, how big is the temperature change going to be? Because it turns out, if it's 2 degrees Celsius, it's one thing. If it's 6 degrees Celsius, it's another, in terms of how dramatically it would influence the planet. In fact, if it's something like 6 degrees Celsius, then we know that in a relatively short period of time, the majority of humanity will have to live in different places. So you know for a fact that it would be massively dislocating to societies. If it's 2 degrees Celsius, it's causing a lot of trouble, but you can manage it. So if you recall, we're trying to get the climate sensitivity. If you double CO2, how much will the temperature change? And I mentioned to you that there were these two estimates of Arrhenius. Well, it turns out today we don't know the number all that much better than when Arrhenius did. Here's a paper that just came out in 2011, and they say, I think the climate sensitivity is a little bit less than what people thought, and these results imply a lower probability of imminent extreme climate change than previously thought. 9 December 2011, a paper in Science Magazine. 9 November 2012. These guys say, oh no, actually I've calculated the climate sensitivity by a different method. I got 4 degrees C for a doubling of CO2. That turns out to be a quite big number. Another paper published in Science Magazine. From which you can conclude the scientists don't know the exact value of the climate sensitivity. Why? Why don't they know? So this is now just one last tricky concept, and then we'll go to more fun things. Well, it's because of the feedbacks, okay? So it's a little bit more complicated. When you put more CO2 into the atmosphere, you'll do things like you'll induce some more water vapor to go into the atmosphere. More water vapor in the atmosphere might create more clouds. If the clouds are very uniformly distributed and they're white, they're going to reflect away sunlight. On the other hand, if you melt ice, which is white, and it becomes black, then that's a positive feedback. So you see, there are many different kinds of feedbacks. And here's one of the conundrums. We can calculate the temperature change with no feedback, and then we can say, okay, the actual temperature change is the temperature change with no feedbacks divided by 1 minus the feedback. Okay? Now, that's just a kind of an arcane formula, but it says if the feedback is a small positive number, then the temperature change will actually be very much like if you only just had the CO2 changing. But if the feedback is positive and close to 1, then the change in temperature could be extremely large. And that produces, if I have a kind of a Gaussian distribution, just a random distribution of possible feedback factors, and then I look at what that leads to ultimately in terms of the distribution of the final outcome of the temperature, it produces a long tail towards the high temperature end. It falls sharply on the low temperature side, but very slowly on the high temperature side. What it means is there's actually a significant probability that the number is up in this 4 or 6 degree range. And despite a lot of effort, people can't bracket this. And that's the honest statement that the scientists have to tell you. They can't totally bracket exactly what the climate sensitivity is. It's a very complex topic. And in the end, we have to live with an uncertainty. There's an uncertainty that says it's possible that the effects due to climate change are ones we could just muddle our way through. Possible at the level of, say, 30%. It's also possible that the effects due to climate change are massively dislocated. Possible at a probability of, say, 30%. Now, if you had a possibility that every time you cross the street, you might actually 30% get hit by a car, you would take measures to change that. Okay? Not going to do this part like clouds. So the answer to this part is we don't know if we can simply adapt to the changes, but there is a significant probability that the changes will be massive enough that we don't want to go through them. Now, just a few more things here. It turns out emissions have to decrease rapidly in order to mitigate climate changes. And they have to decline on the time scale by, say, a significant decrease in the CO2 in the atmosphere by, say, the year 2100. Okay? So, is that possible? Here's some history to look at. This shows what I call carbon intensity. What that means is if I take, I get a certain usable amount of energy, I have to put a certain amount of carbon into the atmosphere to get it. Okay? How much is that? And what you can see is that over time, when we started from our earliest combustion use, like James Watt burning coal, okay? And eventually we got to oil, and it turns out when we burn petroleum, we get a lot more energy for each carbon we put into the atmosphere. Turns out when we go to natural gas, again, we get a lot more energy compared to oil. And of course, where we have to end up is someplace down here. So we need to move down this curve to way, way lower amounts of carbon. And we need to do it by someplace like here, not there. Okay? So looked at this way, it's not impossible. Just something we have to put our minds to. So at Berkeley Lab, there's a whole initiative, many scientists participating, trying to find ways to do this through the Carbon Cycle 2 initiative. Now, I'm just going to take a few minutes and talk with you about what's really happening today to energy. I'll show you two ways in which it looks like it's quite possible that we can make some progress on this problem in the next period of time, not in 100 years, but in 10 years. Okay, so I'm showing two ways in which that may happen. And we show on here Ernie Moniz, who was just appointed Secretary of Energy. All the scientists have a big smile, just like Ernie in this picture, because now it's 2 in a row energy secretaries who actually know everything that I just told you much better than I do. And that's compared to 0 previously. So we're in the right direction, okay? So we're going to talk about 2 quick stories about abrupt changes. They're not going to be as abrupt as you might think, but we're going to see a story for how it is that changes can come about in our energy system. And we're going to look at natural gas from fracking, and we're going to look at solar. Last year, coal consumption in the United States dropped by 12.5%, 1/8 in 1 year, okay? And natural gas went up by 12.5% in that 1 year. In other words, there was a massive shift from coal to natural gas that took place in 1 calendar year. It's astonishing. So now, people in the newspaper will often just imagine that this is because a miracle occurred. But in fact, what happened is research that started in the 1970s. And in the 1970s, under both Ford and Carter, actually. There was an effort afoot to try to figure out how to extract hydrocarbons from places where they were not so abundant, and from places that were hard to get it out from, so-called unconventional gas and oil. And that ultimately started a set of research projects which over 3 decades of systematic research led to an understanding for how to take a drill bit, put it underground, and then follow it with a pressurized stream of water that contains some gritty material and some surfactants, some molecules that help solubilize things, and to induce essentially underground a series of small percussive kind of events which release from very tiny nanoscale pores carbon dioxide, methane that is trapped inside it. Okay, and that's called fracking. So where shale gas comes from actually is a really long period of intensive research, over 30 years of it. And it is working. And here you can see the carbon emissions of the United States as a function of the time. And what you can see here, it is true that there's a recession period, but even if you account for that, what you can see is that actually the amount of CO2 that we're emitting is actually going down a little bit. And that's really an amazing thing. And it's largely due to this natural gas development. And I think it's a positive development. I know there are some people who are concerned about fracking. We can talk about that. But in the end, it's pushing a shift from a form of carbon that is really very energy poor, one that we have to get a unit of energy out of it, we have to put a lot of carbon in the atmosphere, to one where we have to put much less carbon in the atmosphere. So in the short term, this is something that can really make a difference. And let me skip this. I'm going to go now just to the solar story and then wrap up. Now, you know, an important theme of my talk is that very, very fundamental developments in physics are ultimately what underlie our understanding of the planet, but also our understanding of how to get energy. And we talked about wanting to use solar energy. We'd like to use the energy from the sun, ultimately. We'd like to use renewable energy in order to get our energy sources and not be burning hydrocarbons. And so if we look, for example, at solar thermal technology, that of course is based on the science of thermodynamics, but if we look at a photovoltaic, a solar cell, that of course is based on the fundamentals of quantum mechanics. And I just want to remind you, when Einstein won his Nobel Prize, it was for the discovery of the photoelectric effect. How when a photon comes in to hit a solid, it can knock a single electron out. And that was the initial explanation of that, was ultimately the foundation of quantum mechanics. A photovoltaic cell is a solid state version of the photoelectric effect. So it is at the core of quantum mechanics. And the first practicing solar cell was made in 1950 at Bell Laboratories. My back-of-the-envelope estimate is that the cost of making it was a few $100,000 for 1 watt. This shows the price of solar modules as a function of the time as manufacturing has increased in size, in scale. And what you can see is that the prices of making a solar module drop, 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 drop. They come down. Every time you make twice as much, you go down by about 20%. And so that's what's been going on. And it's led to the point where today, actually, the cost of buying a solar module is about 67 cents a watt. So it's well below $1 a watt to make a solar panel. Now, you'll notice these oscillations on here, and these oscillations are supply and demand kind of allocations. And this most recent one, where the price is really dropping very quickly, has come because China decided that they were going to get into solar in a big way. They made a massive investment. They built up a huge number of plants that have the capacity to make solar cells, and so they really essentially flooded the market, and the price is dropping really, really rapidly. I mentioned to you about China. Here you can see this kind of global trends. Here's the United States in 1997 is the largest producer of solar cells. And then you can see here where when China decides we are going to own this market, it only takes them about, 6-7 years, and they are now 2/3 of the production market of solar. Now, solar deployment, the prices have now dropped low enough that in many, many parts and many, many markets, it's actually competitive with any other way of getting energy. First, the natural gas prices influence this a little bit, but fundamentally what you see going on here is how much solar is being installed as a function of time is growing dramatically. Okay? Just more and more solar every year. There was 23 gigawatts installed in 2011. Halfway through 2012, it was already at 27 gigawatts. And so you see this enormous growth. Actually, this number is wrong. It's actually a $77 billion industry today. So it's a $77 billion industry. Nothing to sneeze at. And if this trend continues for just a little bit longer, then in a given year, solar energy will be producing on the order of a terawatt of new capacity each year. And there's about, I think the total energy consumption in the US is in the sort of 12 terawatt range. So, now you're really starting to talk significant amounts. In fact, sometimes people say, well, gosh, there's going to be some limit. We're only going to be able to do so much. Take a look here at what happened in Germany, where with a very explicit and organized policy, they decided to favor renewables. And so what you can see here is on this particular day in May, you can see the amount of energy that they, amount of power that they were getting from solar, and you can see that at the peak of the sun shining on that particular day in Germany, they were getting 40% of their electricity from solar. 40%, okay? Now, you also see it oscillating here. And I don't know if one of this graphic is in here. No, it's not. Often what people will think here was, okay, you picked the one day that Germany happened to have some sun. But in fact, actually, over this, over the 2012 summer, from late April until mid-September, this was a kind of typical number. They got about 14% of electricity over the 24-hour period from solar. During the winter months, they got quite a bit less. So what you see here is, it is a bit crazy to have a system where you get this huge oscillation in the amount of power available to the electrical grid. But in Germany, they're managing it, which people, there was an argument going on at one point that if the amount of oscillation on the grid is more than a certain few percent, it'll knock the whole grid haywire and so on. Obviously not true. But what this does point out more clearly than anything else is the huge energy storage problem. And so ultimately, we want to store the energy. And so where do we want to store the energy? Certainly, you could try to think about batteries, but in the end, it turns out, if you really store the energy in chemical bonds in a molecule, that's the most energy-dense form. One of the reasons we like fossil fuel is because those hydrogen and carbon-carbon bonds, when we combust them, and they store a lot of energy in them per unit volume. So ultimately, what we really want to do is learn to emulate nature and to make an artificial photosynthetic system, which will take sunlight and make a fuel rather than electricity. And that's a project that a lot of people around the world are working on. Berkeley Lab is a joint project with Caltech for an energy innovation hub to do that same thing. You'll remember I mentioned to you, this is one of the last things I'll show, that we have to think about the developing world. And this graphic, the size of a circle is the population. And then you see the CO2 emissions versus income per person. And what you can see is that as countries develop, they get more income per person. They also tend to have more CO2 emissions. And what you need to think about is the fact that this is the United States here, but here's China and here's India, and all these other circles here. And if you add up all of these circles, they're a lot bigger than that one. And they're moving this way, right? So the fact is that over time, one of our biggest challenges is going to be to try to help the developing world to find a pathway to energy usage that doesn't have the same amount of CO2 emissions per person as we are having, and yet still allows them to have a decent development. And that's going to be a huge struggle that we're going to have to figure out how to do. What I want to leave you with is two messages. The first one is that the science of what we know about climate change is sufficiently robust, deep, grounded in core disciplines, that it's not something that we ought to be really having a lot of debate about, but we still are. And the second point is that there's a lot of ways that we can see our way towards making progress on this problem. I showed you the example of natural gas and of solar. If we move towards an energy economy where we really push fully from coal to natural gas, and we brought our renewable fraction up to 10 to 15% by, say, 2025, 2030, we would have made a substantial dent in this problem. It won't be completely solved, but we would have made a lot of progress. And those are achievable things for us to do. So I don't want to leave you with a downer feeling. What I want to leave you with is a feeling that the science community has come to an understanding of how human activity, now for the first time in history, really impacts the planet. But it's also at the same time producing for us the knowledge that we need to avoid the difficult kind of situations that we could get into if we don't pay attention to those problems. And I'd like to thank you for your attention.